And so we end up doing quite a few solutions here for different frequencies, different speeds. You can see that there's a lot of information represented, a lot of simulation effort produced in this result plot here. And I'm really pointing that out to highlight all of the efficiencies that are brought about in the mechanical side by that I'll show next. So we're producing efficient ways to replicate data, and that in the subsequent steps would require a lot more simulation runs for all these different solution points here. But we do those solutions very efficiently. And one of the key updates that is incredibly efficient here, more than 10 times efficient by a default change that was made in the mechanical mapping and the mechanical force transfer. So we have a couple different options. I mentioned before that there were options for object-based force calculations. So we could each tooth calculate a single force, or we can do element-based mapping, where we take the force densities in our magnetic solution and map those force densities to the structural mesh. And this update makes the mapping process and then the solution incredibly efficient. So all of the mapping process sets the solution up to be very efficient is really what I want to draw out here. And so once you get up to the latest versions of 2020 R1 and then soon to be 2020 R2, all of these waterfall diagrams, whether you're using the object-based force transfer, which is really good for most electric machines with a lot of teeth like it has here, or if you're looking at the element-based force mapping, which might show up in some more complicated 3D models, maybe with skew or maybe with something that's not as regular, then it's going to solve very efficiently, because we need to solve a lot of points for frequencies and speeds, but the efficiencies here in the new versions make that very accessible. And so then to go beyond what, so I was describing the equivalent radiated power waterfall diagram. And if we want to go beyond that, and we want to put a microphone at a specific point and calculate the sound pressure level at that microphone, then we can always do a harmonic acoustic analysis and do the same thing. It will automatically transfer the vibration response, and it will automatically transfer the analysis setup details so that we can get the waterfall plot for the sound pressure level and include any other type of radiated sound or propagation or reflection type of dynamics. So that's all nice. I mean, that's what we need, is to get these plots, to get a lot of quantitative data. And of course, we can export that to CSV files. We can post-process that in our other Ansys tools, look at the order lines, optimize over the orders. We've done a lot of quantitative analysis, but we also want you to hear what that sounds like. So starting in 2020 R1, we have a right-click option to automatically export a wave file. And so we can take individual speeds or this whole ramp up for the waterfall diagram, and we can listen to what that noise sounds like. So if and I'm going to warn you that I'll play a sound. It might be a little loud, so just be prepared for if this is too loud. Okay, so that's an example of the ramp up of this noise, and it was entirely created just by exporting to a WAV file. And that's a very nice thing, of course, for the engineers to have, to show their management, to show their customers, and to really understand at a first level what their design and simulation steps have produced. The other option right below that is an option to export to VR experience sound. And I really want to highlight this, and I'll go back to my pitch at the beginning of this talk, that there are some very good webinars that are already on the Ansys resource library for VR experience sound. It's an Ansys product for understanding the sound, understanding and being able to manipulate the different orders. So what we can do is have, there have been some very good webinars and examples of a motor that's connected to a fan, and we can take that actual measured sound from a microphone, subtract out the motor, and then plug back in a new simulated motor. So then we're combining sounds from your measured data with your simulated data. And that's an example. There are other ways that we can use transfer functions and transfer paths within the VR experience tools. And this export is a really nice update at 2020 R1, but there are some new tools at 2020 R2 that will make this more like a studio to very, very easily combine these different sounds and to manipulate them in some very intuitive ways. So please look into this, look into the webinars that are existing, and then stay tuned for 2020 R2, which will, I think, provide a lot of really interesting things for electric machine designers. Now, I'm going to step away real quick from the Workbench workflow and mention a new connection that is also very exciting. So we have one tool called Ansys Motion that has some dedicated simulation tools for gearboxes, and housing, and lots of things to do with gears and bearings. And so Ansys Motion is a really good fit for any electric machine cases that are connected into gearboxes and housing. And we are working on workflows to be able to connect the forces from Maxwell directly into these motor housing gearbox type of simulation models. And so we do have some connections that are built in now, some ways to export the force files, and then we are working on improving this and making the workflow more seamless. So if you have gearboxes, please keep your eye out for this. And this is just another quick highlight of what that could look like, where we see the forces imported into our Ansys Motion tool, and then we see the motor plus gear plus housing type of response here. And so this is going to be really interesting and powerful for these gearbox workflows. Okay, so let me go back on the magnetic induced noise side and look at an example. And we'll walk through this example so that we can see what this workflow looks like, as well as what type of information we can get from it, or how far we can push it. So in this example, I'm going to look at an IPM machine with skew, and so we can represent it, of course, in 3D like this, where we see the flux on the skewed rotor is sort of following the rotor skew here. So that might look like this in terms of the magnets stacked up on top of each other. And we can look at cases where maybe there's PWM switching currents connected between the motor and the drive. So we can solve this motor, whether it's a multi-slice skew model, or maybe it's an equivalent circuit model with skew included, or it's a full 3D motor model connected to the electric drive. And then the information from all those layers of the skew can be mapped in many different ways to the mechanical structural model. And so this is one representation of connecting all the forces from different layers of the motor model to the different layers. And of course, with the electric drive, we can look at these type of current transients. We can run it out, especially with equivalent circuit models. We can run this very efficiently, get that steady state current, or we can look at initial transients. There are lots of different things that we can look at here. But what I did here is I connected up a equivalent circuit model, ran it with some PWM switching at 4 kilohertz across 6 different speeds from 500 RPM to 3000 RPM, and ran it out to steady state, and then used the last electrical cycle at steady state to calculate the forces. And so I'll get back into what that means for us, what that looks like. But to really drive home the point here about the efficiencies that we have built into our workflow, I'm going to show you a comparison that our mechanical team did on this example model to compare the full harmonic solution in our structural mechanical solver to the modal superposition solution in the harmonic analysis solver. And that there are a lot of good built-in tools to evaluate that your modal superposition is going to be sufficiently supported. Okay, so what I mean by that, the plot on the right shows 3 curves. The blue curve is the full harmonic solution, so we're using the full solver. It's not making any approximations in the solver itself. The gray and the yellow are using the modal superposition analysis, where the yellow has a low number of modes, like 30 modes. And the gray is using 150 modes. And there are a lot of best practices that our mechanical engineers can tell you about looking at things like participation factors, to look like the mass, the rotational contributions of the different modes, as well as the frequency range of those modal solutions that will then be used to support the harmonic analysis. So if we get modal solutions that are only predicting up to 4 kilohertz or 5 kilohertz, but we're running this whole sweep up to 10 kilohertz, that modal analysis is not going to be sufficient. So we get all that information on the mechanical side by running this modal analysis as the precursor to the forced harmonic. And there's a lot of information about how to analyze that, how to look at the setup for that. Some of those are incorporated in those workshops in the Ansys Learning Hub examples that I gave, as well as reaching out to the Ansys mechanical support team for just finding out best practices for looking at these type of analyses. So I'm putting a lot of information on this modal superposition setup. And what this gets us is that it is much faster to solve many frequencies and many speeds. And it's even faster in 2020 R2 or 2020 R1 for both object-based forces and element-based forces. So please don't all of these things together really allow us to give an efficient and accurate workflow that we have used for quite a few different customer models, as well as examples in our test suite. The result of running these PWM excited models through Maxwell at 6 different speeds, and then running those results through the structural model with the equivalent radiative power produces this type of information. We have, first off, a waterfall diagram that's showing the PWM noise around 4 kilohertz. Of course, there's a lot of other structural interactions that are, I'd say that they're between maybe 5 and 7 kilohertz is where I saw, I think, most of the structural type of response. But we definitely see a lot of interaction going on around 4 kilohertz, which was the PWM switching frequency. And I'll give you the warning again. I'll play some sounds here that might be a little loud. I turned it up a little bit so that you can hear the differences, hopefully. And so I'll play a sequence of sounds going in order from 500 RPM to 3000 RPM. So, and of course, if you could hear those sounds, that they do increase in sort of a harmonic octave-like progression, but there's a lot more detail in there as well. So I'll play again the maybe 2000 RPM and the 500 RPM, because I think there's some really subtle detail in here that shows that maybe the 2000 RPM is a little bit more, so that's up here. Maybe there's a little bit more pure tonal difference between this 4. I mean, it's a little stronger interaction at that 2000 RPM, the fundamental, and we don't hear as much from the PWM. But the 500 RPM, there's less interaction at the fundamental, and we're just about getting only the PWM switching. So I'll play those again, and hopefully you'll hear just a little bit of that subtlety. In fact, I think this 500 RPM is just about only the PWM switching, and we could, so anyways, there's some interesting stuff going on there just from these wave files. And I haven't even pushed it into one of our sound tools like VR Experience. The other thing that we export again is the full waterfall diagram, which we can hear the ramp up here. Okay, so that's just like a smooth ramp up following the orders. And it starts off pretty quiet, but then, of course, picks up on all the noise at the higher speeds. So lots of different approaches here. We can definitely bring together the resources of magnetic design engineers for electric machines, these commutating noises, the efforts to reduce harmonics in the machines, to reduce torque ripple and things like that, and the effects that that lead to on the structural vibration and these sounds here. So in conclusion, we have this end-to-end workflow for looking at many different aspects of electric machine NVH. And we try to make it both as flexible as possible, as well as being efficient and accurate. And I think that many of the updates that we've had over the last couple releases of Maxwell and Mechanical make this more powerful, more efficient, more easier to see all these vibrations and acoustic responses, and especially to hear and perceive the noise, and then to push it off to the next level of either the acoustic analysis or the noise perception analysis to see what that would look like inside of a real model. So I hope you get a chance to check this out. I hope you learned a little bit about our workflow and some of the updates we've had. You can always check it out by reaching your Ansys team and getting started by looking at the Ansys Learning Hub.